Here in the first slide, some beautiful pictures just to enhance the enthusiasm to start the presentation. And here I have the three sets of telescopes and skies that I analyzed in my thesis. So here is the FLT that I used to observe the whole Milky Way. Here is NTD Massilia that I used to observe the bulge in specific cluster. And here is solar telescope that I used to observe the small Magellanic Cloud here. These two pictures are real pictures, but this one is colored because actually this is the north part of solar cartoon. So I just put the Magellanic Clouds behind the telescope just to highlight that. And in my thesis, I studied globular clusters, star clusters, so I show another picture of one specific one just to show another beautiful. This one is 47 too. And I show here zoom of this cluster, just to show that I analyzed some individual stars in star clusters in the context of the formation and evolution of the galaxies. So this is what I said. Okay, so the presentation will be like a summary of the thesis, because the thesis is very dense. There are many things to discuss there and discuss later. And here I just show a brief introduction concerning the Milky Way and Magellanic Clouds, because I'm studying formation and evolution of galaxies, looking into star clusters. But I just use two galaxies, it's the Milky Way and small Magellanic Clouds. And then I start with the small Magellanic Cloud, and then a huge portion of the thesis is this survey of globular clusters in the Milky Way. So I will spend some time with this survey here. Finally, I will discuss a specific interesting cluster in the bulge, HQ1, and then we'll finish with a summary and the perspectives. So let's start with the introduction. So a basic question to understand the universe is how did galaxies form and evolve? And there are two ways to answer this question. One of them is to observe many galaxies in different redshifts and try to tell the story of what happened with this galaxy. Another thing, and this is what we do here, is to observe close galaxies and observe different objects and stellar populations with different ages and try to recover what happened with these galaxies and try to set these galaxies as examples of what happens in general. So here we choose our home galaxy, the Milky Way, and also the Magellanic Clouds that are here in the neighborhood of our galaxy. So this is an old sky picture centered in the Milky Way here, just to show, to tell about this story. So roughly, you can think of an initial collapse of a giant molecular cloud that started to form stars at the beginning of the universe, the Milky Way. And in the outskirts of this cloud, there were some bumps of condensed gas that started to form stars, and it formed the halo. And the bulge is the central part of the Milky Way, which is more dense, so it should have more efficient star formation. And finally, you have the disk, which has from the shape of the disk actually, seen from above, and it rotates because of conserved angular momentum. However, the bulge is not exactly a spherical thing. There is a artistic view from above from our Milky Way, showing the arms and so on. Our sun is located here, and there is a bar shape in the middle of Milky Way. And this bar shape is a dynamical structure that could bring some stars from the inner disk towards the center parts of the Milky Way. So this would mix populations. So the both stars, stellar populations, should have old stars and inner disk-like stars. And some studies should do this detail. And there is more. Recently, it was found that this inner region is not spherical only. There is a bar, but it has also an X shape in the very inner part coming back to the previous image. So there is an X shape in this direction. So it's parallel to the bar, but there is a three-dimensional structure. And this is being studied by models, observations of stars, and many other stuff. So there is some complexities in the boat, that's the point. Concerning the Magellanic Clouds here, there is a beautiful gas structure here. And this coincides with an orbit around the almost polar. And observing the velocities of this gas, it was shown that this is a trailing structure and this is a leading structure. This is called Magellanic Stream and this is leading arm. So here is the large Magellanic Cloud and small Magellanic Cloud. Okay, so there are some scenarios for that. If you are thinking about interactions between galaxies, you have to think about some models to explain that. And the models here that are more discussed are room pressure and tidal stripping. So room pressure basically traces the gas back the orbit here, and it would not explain the structures in front of the orbit. And the tidal stripping will mix both gas here and also stars, and will explain the two structures. So these gas structures were found, and the finding of these structures here was a confirmation, because the Magellanic Stream is known for 40 years, but the confirmation of this leading arm resulted in a Nature paper, and it's very important. So the confirmation of a stellar counterpart of these gas structures would be very useful to confirm or to endorse some models towards tidal stripping. That's what we do here also with the star clusters in the Magellanic Cloud. Okay, so as I mentioned, I studied the stellar populations in these galaxies, but specifically using star clusters. So the star clusters, in particular in the small Magellanic Cloud, can be used to discuss this tidal stripping. Okay, so we use solar telescope to observe some star clusters, and here I show a real image, of course in false colors. And the region of a star cluster is not as huge as the globular cluster for Saviane, as I showed. It's less massive. But I show here that in the field of view of SOAR, it's very useful for this kind of observation, because you have here the region of the star cluster, and you have a correlated field here that you can use as test. As I showed here in the right panel, there is a CMD, the color magnitude diagram, in the region of the cluster, in the circle here, and outside another region to call as field, color magnitude diagram. And we use this CMDs to derive probability of each star here to belong to the cluster, because you have pollution of foreground and background stars. So in black are the most probable stars to be members of the cluster. Once you have that, we compare our observed CMD with a grid of synthetic CMDs to find the parameters of this star cluster. And we do that as follows. To simulate a CMD, we start with an isochrone, the stellar evolution models, which means to choose an age in metallicity. And we just move this isochrone using some information of distance and radius. Later, we put some stars here following an IMF, initial mass function, to distribute the stars of different masses here. Of course, cutting some magnitudes here to be consistent with the observations. There is no reason to simulate stars that will not be compared. And introduce here also the photometric errors equally to the observations. And finally, we do a Hess diagram with the density of this, which will be seen as probability. So we can just put our observed CMD in front of it and derive a likelihood for that. So we proceed as that for a grid varying age, metallicity, distance, and radius. So we vary these 4 parameters, do a grid, compare our observed CMD with everything, and find the best fit or with the distribution of the likelihood. So I'm showing here an example of a best fit for CMD. Here is the observed one with this color code here for the probability of membership. So remember that black is the most probable. And here is a synthetic CMD with the isochrones that were used to produce the synthetic CMD here. So just to show that it's quite similar. Of course, we have some stars that could be boost travelers or something else. Okay, so looking to the whole small Magellanic Cloud, it's plotted here. All points here are star clusters from Beatriz and collaborators catalog. And I highlight here in the middle in gray a main body of the galaxy, which has a ellipsoidal, more light shape. It's not circular, that's why I use these ellipses here as distance from the center indicators, not as radial distance because of this shape. And if we highlight this main body, you can see that there are some structures here in green, yellow, and blue. And this structure should be related to that gas structures that was the tidal stripping issue that I discussed before. So this is clearly related to the bridge. There is a bridge of gas between the 2 clouds. So this is the small Magellanic Cloud, and the large Magellanic Cloud would be here. And this other one is predicted by models. It's a counter bridge that's behind the galaxy. And here, it's a group of star clusters that we call West Halo. And we argued here in this thesis, in the paper, that this star cluster should be related with some tidal stripping gravitational issues here. And the way we study here is looking to these clusters. We have 4 clusters falling in this region. There is another one here. But looking specifically on these ones, the first thing is to analyze if all clusters follow a same chemical enrichment pattern. So there is all clusters here are from the same small Magellanic Clouds. In red, I show the studied by us, and in blue are the West Halo clusters. In black, here in the line in black, I showed a model from Beatriz and Saviane, just to show that this theoretical model follows roughly the trends of the distribution of age and metallicity here. However, in this region, it seems to have a dispersion of metallicity. So it should have some complexities also in this galaxy. But the important thing is to show that all clusters are following the same age-metallicity relation. Which means that they should be of the same galaxy. And here is the part of the tidal stripping. So the thing of age and metallicity here is the distance indicator. It's basically the ellipsis thing. And I show here, I highlight the blue points together with the red points here that were observed by us. Here we can clearly see that there is a gradient in age. For metallicity, it's not so clear, but it seems to have a trend. And this is consistent with a stripping of star clusters from the center, because you can see that as far as the cluster is, the more old the cluster is. So the clusters that were formed before, early, they were already stripped, and now the other ones are being stripped also. And for metallists, the more metal core here would be formed before. So if this gradient is confirmed, it also confirms some tidal stripping in this galaxy because of the Magellanic Clouds and Milky Way interactions. So this is a good result when we are observing more clusters in this region. So these results are already published in this paper. You can check. Okay, so as I told you, the huge part of the thesis, the core, I spent a lot of time on this, is this force 2 survey of the globular clusters in the Milky Way. So we target 1/3 of all globular clusters that are cataloged in the Milky Way. So it's a huge amount of clusters and statistically significant. And the clusters are distributed like this. These letters means the components, they're really long. So they are distributed along both this inner and outer halo. So they covers all the populations and all the area here. So we can derive many things from this data. The other thing from the selection of the clusters is that we target more distance or highly radiant clusters that usually are not so studied as the bright and massive and close clusters. But thinking about the whole picture of a galaxy, you have to study all clusters, not only the most bright. And here just show both these inner and outer halo clusters, just to show that we cover radioning from almost nothing up to 1.5 more or less, and distance from solar neighborhood up to outer halo 18 kiloparsecs. So just show that our method can derive parameters for all kind of clusters here. And another important issue, if you want to discuss Asian-metallist relations and the whole picture of formation evolution of the Milky Way, we cover the whole range of metallists for globular clusters in the Milky Way. That is shown here. This color, in colors here. The gray is the whole center. Okay, if the clusters are distant in high gradient, it means that they are faint. So we studied middle stars, but targeting the brightest stars, the RGB, the red giant stars here, the red giant range. This is a CNT that we use from a prey image to select the targets to observe spectra of each star. And here is the distribution in the sky of the stars selected for observations. So they have to be distributed in the sky to fit the slits in the instrument. But also, we force to distribute the stars to avoid any biases, to conclude something that's reduced. Okay, so the observations were carried out in Bonato, using force 2 instrument. And we have more or less 20 red giant stars per cluster. And we observe in this optical region and also in the near infrared, in the concentric, in a resolution of 1000. In this thesis, I studied and analyzed all the set of spectra for the whole 51 clusters. And this other set of spectra were analyzed by our group. There is a paper from Evo from 2012. The other one's being prepared. And here's some statistics of the whole the total sample of spectra is more than 800. I had to analyze that and check it by eye one by one many times. So more than a half of this spectra were classified as members of some star clusters. And the others were classified as non-membered, as few stars, or some few spectra were not useful because of observation issues. Okay, so the method that we use to derive parameters from these individual star spectra were like that. We have in this spectral region many iron feathers, and also we have this strong feather of magnesium. So in another thing, many lines here, many feathers, are sensitive to gravity and temperature. So we can derive temperature, gravity, metallicity, and an alpha indicator which is based on magnesium. So it's a very powerful region, spectral region. And the way we do that is different from that is used from people who are using high resolution spectroscopy. Usually these people use like a equivalent width of specific atomic lines of iron to derive metallicity, for instance. But in this resolution, we don't have a specific line to derive this. In this resolution, when people have gradient spectra, they usually choose the indices, which is they choose some specific regions of the spectra that are more sensitive to something like magnesium, the triplet of magnesium here. Okay, but here we have individual stellar spectra, and you have a bunch of libraries of stellar spectra that you can compare and try to find the parameters. And we have a lot of information in the whole spectral region. So why not to use everything? That's what we did here. And here I show an example of a full spectral fitting of a metal-rich star and a metal-poor star. And here is the residual. In black is the observed spectrum, and red is a library template spectrum. At best fit this. Okay, so we have to choose the libraries. And there are two kinds of stellar spectral libraries. It's a syntactic library or an observed library. And each one of them has this good and bad things. In syntactic libraries, you have the advantage that you can produce any spectra with any parameters you want, because you're modeling that. However, for metal-rich stars, there are some limitations, because there are many weak lines that are not taken into account. And so the continuum of the spectrum is not low as the real spectrum expected for this metal-rich region. For observed spectrum, we have on the other hand real spectrum of real stars. So many effects that we don't know yet, for instance, they are there represented, even if you don't know they are real. So you can compare real stars, real spectra with real spectra and find a good match. However, the parameters are limited to the availability of stars that we observe. So basically, for this library spectra here, it's basically solar neighborhood stars. And we don't have here, for instance, metal-rich alpha-enhanced stars as we have in the book. So to represent these stars is difficult with this observed spectra in this kind of design. So we used the two of them, trying to compensate the effects of these two libraries in the results. Of course, we have to test our method and to validate, to show that it's good enough and that you can trust in the results. So we use here very well known spectra from Elodie library. So this library is high silent noise and high resolution. So we degrade the spectra to our resolution of 42 and proceed with our full spectrum fitting to find the best fit of the library. And we use for this spectrum, Pastel is a catalog from literature for well-known stars, contemplating also Elodie stars. And you take these parameters as reference that are in the x-axis here. So we have temperature, iron, metallicity, and gravity here. So this is the Pastel parameters, and this is our derivations. So you can see that for the whole range of temperatures and gravities for recognized stars, and the whole set of metallicities, we can derive properly the parameters. And here is the residuals, and the sigma is here. So less than 100 Kelvin, 0.04 DAX for metallicities, and 0.16 for gravity. So it's very good, so we trusted the method and could go ahead. So we applied this method to our set of clusters. And after applying that, we have to just check the results to see if they are consistent, intrinsic consistent. And more than that, we are comparing here also the libraries. As I told you, Miles is the observed library, and Coelho is the synthetic one. So we are comparing here also the results from these libraries, discussing also the issues that I mentioned. So here is the temperature and gravity plotted in a HR diagram. And these isochrones are with literature parameters, just to have a reference. It's not a fit or anything. It's just to have a reference if our results are following the same trends. And here we have temperature and gravity from Miles and from Coelho. And here is the average of these two results. You can see that here the Miles results are more shrink in the region. And this is why, this is because Thesis 8 is a metal poor cluster. And a metal poor cluster, metal poor stars, when compared with Miles, has very few stars as reference. So the average is biased in this region, because there are more stars in this region for metal poor stars. And Coelho is more spread here over the isochrone also. So the two are constant with the isochrones, however, this is more tricky. So the average seems to be more fitted to the strength of the isochrone. For metallicity, we use as comparison values another work. As I mentioned, all stars analyzed here were also observed in the calcium triplet region. And these stars were analyzed, and calcium triplet, calcium is an alpha. There is many limitations to derive metallicity from that, but the results were scaled to a high resolution spectroscopy metallicity scale. So we found that was fair to compare our results with them, because we have star by star comparison. And here I show the calcium triplets in this axis and my results in this axis. And here's the Maya results, again, Coelho results, and the average of the two, as we took the average from temperature and gravity, also from metallicity, because we derive all parameters at the same time. And here is just another trial to pick or Miles or Coelho for some regimes of metallicity, because you can see that for Miles, metal rich are better, so you just choose metal rich, and metal poor are better for Coelho, so you choose Coelho here. However, the average is very good in the comparison, so we picked the average of the two libraries. Okay, we also compared our individual results for each star with some high resolution spectroscopic works. We studied here for the testing method 6 clusters, as I showed in this. We have studied 6 clusters to cover the whole metallicity range here. But only for 3 clusters, we found a coincidence, a match of some common stars, in other words. And for these stars, the metallicity, temperature, and gravities are okay. I just have a comment about Thesis 8 that there was discussed a lot in the thesis that we can discuss later, but it's okay with some comments. And all these tests and the methods present in this paper that was submitted in this it's under discussion with the referee. It's already accepted after some improvements in the database. Okay, so let's go for the whole sample of cluster. As I mentioned, the cost computed was calibrated with a high resolution metallicity scale. So we used the same metallicity scale to calibrate our results, or at least to check if it's already in the scale. Carreta et al. 2009 published a set of 19 globular clusters in the Milky Way, observed 100 stars per cluster with very high resolution. So the results are very good for each cluster and very well constrained. And we have 13 clusters in common, so we can compare our clusters with them. And these 13 clusters covers also the whole metallicity range, so it's very good to drive a scale here. And here is this work, and this is the Carreta derivations. You can see that it follows very well the trains here, with some trains for metal rich. That this is due to some issues with the metal rich stars that they comment from the libraries. So we use some synthetic and observed libraries that there are some constraints for metal rich stars. And that's why we are doing this, just to compensate this small trend here. That you can see that's a 0.1, 0.2, that it's not a huge difference if you're taking this. And this is the scale calibrated. Okay, and if we apply this scale to calibrate the whole sample of the 51 clusters, you can see here a very nice plot comparing our results with the Carreta calibration. Carreta calibrated the whole sample of clusters that are available in literature using some other homogeneous works based on low resolution spectroscopic results, metallistics. And in black here, we are showing all clusters that are common with our work and the calibration of Carreta. However, we see that the 13 clusters that Carreta really observed, we have a dispersion in the residual of 0.07x, which is really, really good. And for the 51 clusters, we have a higher dispersion. That means that this higher dispersion is due to the average of many other works in lower resolution and so on. So we can trust that our results are very, very good and compatible with high resolution. And there are some other 6 clusters here that were not calibrated by Carreta and were observed by us. So we are contributing with 6 new clusters. Another issue here is the bimodal distribution, metallicity distribution, that are covered by our results. This is a common characteristic of galaxies. Okay, as I mentioned, we derived also magnesium, so an alpha indicator. And we have, I mentioned that we have this issue with the metallicity, that is because of the library. And for magnesium, I mentioned also that magnesium is obtained only from Mayo's library. And I mentioned that from Mayo's library we have basically solar neighborhood stars. So we have to compensate also for metal-rich stars. If there are some stars that were metal-rich and alpha-enhanced, we have to compensate this and calibrate. So the procedure is as follows. We take this formula from Solaris. This is the total metallicity of a star that takes into account the metallicity based on iron plus a factor that's proportional to magnesium. What we do here is to keep fix this total metallicity for a given star and assume that the variation in metallicity that I showed in that plot is compensated by the variation in alpha. So there is no reason to believe that the total metallicity will change. We just had a bias in the metallicity results due to this magnesium abundance because of the constraints in the library, just because of that. So here we're just compensating the limitations of the library. And here we proceed as follows: just take the difference between the uncalibrated and the calibrated values, and we can isolate this to have final magnesium calibrated, compensating this. So for the metal pool, basically there will be no changing, and only for the metal rich will be like a small shift to compensate that. Okay, also have everything calibrated and well done and compared. So with just in our results, you can check how these results can tell us about the chemical history of the Milky Way or some formation and evolution of this galaxy. Just to remember, the chemical enrichment via supernova explosion, looking into this plot that I use a lot here. We have here iron, metallicity, and alpha over iron. And here we use magnesium. So, the beginning, supernova type 2 explode the massive stars and release some alpha elements, and you have a fixed ratio of alpha over R. When the supernova type 2 starts to become important, we have a decrease of this ratio because it releases more iron peak elements, so this ratio decreases. And this knee here will tell us how efficient is the star formation of the galaxy. Because if the star formation is very efficient, the time for supernova type 1a to become important, we will give time to the supernova type 2 to enrich the environment of too high metallicity. Otherwise, the heat will be lower. So here, it's our data. Looking into this plot in the scenario of alpha, based on magnesium, and metallicity. So you have this like supernova type 2 here and supernova type 1a here. And I show 4 plots for the 4 components of the Milky Way. So here's bulge, this inner and outer halo. In gray and green, I show in the 4 plots filled stars. And in black, I show my results for the 51 clusters split in the 4 panels, the 4 components. And the first thing that you can see from this plot is that the compatibility of globular clusters with filled stars, which for the 4 components, which indicates that the globular clusters and the filled stars should have experienced a similar star formation environment. So all globular clusters should have been formed together with the Milky Way or some related environment. Another thing is that this knee that I call the attention seems to be the same for the 4 components and close to metallicity -1. So this is an important constraint. And another last thing is that bulge in this cluster seems to be more towards metal rich, and inner and outer halos seems to be more metal poor. Okay, so we can compare these results with age of these clusters to have a time scale in mind and try to trace some picture of the galaxy. Here I took some ages from a recent work of Univ that's an homogeneous set of ages. However, not all clusters are in common, so I have a few clusters here, not the whole sample. Okay, so first of all, you can see here in this first plot, age and metallicity. Okay, so the metallicity -1 here would be the startup of the supernova type 1a. And you can see that this takes, if you take from here to here more or less, for -1, in average, roughly 1 giga-year. So I would say that the time scale of supernova type 1a to become important in the Milky Way environment is 1 gigayear. So this is important to constrain some models of chemical enrichment of the galaxy, because this time scale can vary a lot from different galaxies. Another thing interesting here is that the blue points here are golden disk clusters, and the red points here are halo clusters. It seems that the blue points are more metal-rich than the red points. And what this indicates, if we pick an age, we see that for a given age, bulge and disk cluster are more metal-rich than halo cluster. And this can be explained in some ways. One way is this initial collapse that I mentioned before, that the bulge is in the inner part, more dense gas, and more efficient star formation. So at the same time, they could be formed. However, the bulge stellar content would be more metal-rich and more fast enriched than halo. Other scenarios could say that many stars in the halo were formed in low efficient star formation that could be dwarf galaxies, for instance, that were captured by the Milky Way and then disrupted and formed part of the halo. This is a regular discussion, so these are some results that our work can give, comparing with age and then magnesium versus iron. And here is the magnesium also, because we have magnesium, so this we can compare also with that. So thinking that bulge is more efficient, this means that the magnesium should be higher, or the niche should be different. But you can see here in the previous slide that the niche seems to be the same for all of them. Although the green dots for field stars seems to be higher than these, for instance, but this is very, very subtle. And here we cannot see any difference, or it's hard to see difference between halo and bulge clusters. So this is another discussion, but it's a very interesting point that we result from our work. Another issue is this that I mentioned from capture of dwarf galaxies to halo, to the Milky Way. So we have some clusters with multiple populations. So it's well known nowadays that all globular clusters have multiple populations thinking on, or multiple or spread in light elements abundance. However, for iron peak or overall metallicity, this is not the case for all clusters. So here I just show that for the brightest and more massive clusters, this is the case. And I highlight here the all the cases are known in Milky Way, and we study in this work these two clusters. Just to remember that we have no bias in the observations in all the right triangle brains. And here is the distribution of metallicity and magnesium. So for metallicity and magnesium have a bimodal distribution. There is a main peak here of metallicity and a secondary peak here. And the blue and red Gaussians here are the distributions thinking that there would not be a metallicity spread. So just considering the uncertainties in the individual measurements. Just for a visual reference to show that this bimodality here is real. And another thing that we can derive from our results is in this plot again for magnesium versus iron. So we have that as supernova type 2 and type 1A for the Milky Way and for a bunch of dwarf galaxies. Just to compare and see here that if there is an extragalactic origin for this cluster, which means that it was formed inside a dwarf galaxy and then distributed and captured by the Milky Way, it should have a chemical enrichment pattern of a dwarf galaxy. So that's why we compare here with a dwarf galaxy also. it seems, although there is some dispersion here, it could be compatible. We would expect something like inclined here. And for the Milky Way, it's compatible with this trend. So there is no spread in magnesium in trends, and for iron, yeah, it is. So it's difficult to say if M22 has an extragalactic origin or no from this plot, but it seems that at least it was formed, if not in the Milky Way, in a similar efficient star formation galaxy. In the other cluster, we have fewer stars here, and the same plot again. Here it's harder to see. So we have this main peak here. These other are less important because it's 1 or 2 stars, so it could conclude something. And these Gaussians again for reference. So with our uncertainties in our few stars, it's hard to say that there is multiple populations here. It's the same thing for the magnesium over. But there is another work from our group, I'm not part of this paper, but they found with more statistics for stars that there is a metallicity spread in this cluster. And this peak is actually split in 3. So it's very subtle. And this cluster is probable has an extragalactic origin because it's compatible with the orbit of a stellar stream recently discovered that should be due to a destruction of a dwarf galaxy. Okay, so finally I'll talk about a very interesting cluster in the book. It's H21. And I'll tell you why it's important. But before, I will just remind you about the shape, the morphology of the horizontal branch. In the polar magnitude diagram, have these horizontal branch stars. And this is some simulations. Here in the left panel, keeping the age fixed, we know this work, they vary the metallicity, showing that as more metal core, as bluer the horizontal branch is. And on the other hand, for a fixed metallicity, as older, as bluer it is. Of course, it's not 16 gigayears, but it's the model just to show that it's older. And HP1, we studied in our first field survey, and we derived this metallicity already calibrated. And this metallicity should present a horizontal branch like that for like an old age. And we know that from observations that HP1 has not a horizontal branch like that, but like this one, or blue, which would mean that if you assume that it's just an effect of age, that this cluster should be the oldest object in the Milky Way, or at least one of the oldest. Okay, here is the CMD, the polar magnitude diagram for the cluster, so we cannot see the main sequence turn off here, but you can see here the right giant branch and the blue horizontal branch here, and here the stability strip where I can find some candidates of variable stars. And here, if you think that this could be the oldest object, you of course have to derive the age based on a turn-on on a CMD, for instance. And we try to observe these in Hubble, for instance, to observe to derive some ages. But as you may know, the derivation of age is sensitive to the distance. As I showed, for instance, in the beginning of the presentation for other work, that the distance can move the CMD and the polar and magnitude of the stars. So it's quite important to derive precisely the distance of this cluster to have a very well constrained age. So we've taken these RRU candidates because they are distance indicators. And we derive light curves for them here. This is the variability of the magnitude. This is the magnitude of the star over time. This is the phase. And here's the variability of the star. So the period of this variability against the magnitude, the luminosity of the star, you can use the period luminosity relation to some coefficients from the literature and derive their ages. And we confirm 3 stars as properly are here. And the distance that we derived from them is 8 kiloparsec. This confirms that this cluster is the innermost object known of the galaxy. And this is the candidate to be the oldest object of the galaxy. So this means that the oldest globular cluster, not the other object, could have others below stars, but the oldest globular cluster in the Milky Way should be in the very inner part of the bulge, and should be this cluster. Okay, so we'll finish with a summary and some perspectives. Just to remember the overall scenario. So we studied SMC clusters with Magellanic Clouds, specifically in the west halo. So there are gradients in age and possible in metallicity, which have consequences in tidal stripping models against the ground pressure. For the survey of globular clusters in the Milky Way, we derived iron, metallicities, and magnesium thinking on alpha for 51 clusters, which is 1/3 of the sample in the Milky Way. 6 of them are new concerning the calibration of Mg. Clusters include stars are following the same chemical arrangement pattern, and bulge should be more efficient than halo, and this could have to be discussed more. And this could be explained by this initial collapse with different efficiency plus this dwarf spheroidal galaxies contributions to the halo components. More of this survey, we studied 2 interesting clusters with multiple populations regarding metallicities and magnesium, and they have possible extragalactic origin, taking again on this disruption of dwarf galaxies in the halo. And observe also some variable stars in H21, the bulge cluster. That's a candidate to be the oldest cluster in the bulge, with a distance from us of 8 kiloparsecs, so confirming that's the inner part of the bulge, which constrains very well the age. So some perspectives in the near future work that's already been working on. So there are for the SMC, we observed in this thesis these blue clusters here in the west halo. And last year, I went to solar telescope again and observed these other clusters highlighted in red here. So they are red under analysis. So they are properly homogeneous and complete set of gradients, metallicity and ages. The other gray points here are red published in literature, so it can complement and put on the same scale. For the survey of globular clusters, we have a list of things that are already thinking on the papers. So the paper 1 method is already discussing with the referee, and the capture 4 thinking on the whole sample of cluster and discussion against ages and the scenarios of formation should be prepared soon for paper 2. And the capture 5 for multiple population clusters, the M22 and 5824, should prepare for paper 3. And another thing that we can think is using the pre-images that we use just for selection of the red giant stars to derive the ages of these clusters. Because as I told you, there is no coincidence of all sample of these clusters with the homogeneous derivation of ages. So we could do that and derive a whole picture. And from our lyric, Sergio Ortolani is now in Massilia observing more images for this cluster to derive a very well sampled light curve and to constrain very well the distance. And then the age should also compare with some VVB survey. We are members of this survey, so we have access to other band units, so we can derive also other light curves and confirm very well the distance. Should prepare also, I didn't put here, a proposal for Google to observe the CMD reaching the term of the CMD to derive the H, and prepare out through this capture person. And that's it.
Thank you.